Hi folks. Today we're going to learn the key technique for Chapter 3. But before we go there, I do want to mention why we're doing all the stuff that we're going to do today. So from our investigation the other day, we saw what happens when we factor a polynomial. It gets easier to graph. And once we know the end behavior, then we can probably generate a decent graph of complicated polynomials as long as we can factor them. So the two big questions are how do we factor, and once we factor, how do we know what's left over? And I want to look at that in the context of this example. So right here we have a cubic of x cubed minus 6x minus 8. It does indeed factor to this expression over here. And I can show that just by multiplying out this one, by, quote, foiling it out. So I'd get x cubed plus 5x squared plus 4x. Okay, and then all the other ones, minus 2x squared minus 10x minus 8. Okay, collect all your like terms, and we're going to get this, which is the same as what we started with. And this really brings us back to some grade 10 stuff. When we first learned how to factor, it was kind of a mystery how to do it. And for some, it's still a bit confusing. So doing this, expanding out or multiplying out, is typically easier than factoring. Going from those two brackets to x squared minus x minus 2 is easier than going from x squared minus x minus 2 and going, ooh, I wonder what multiplies to negative 2 and adds to negative 1. Ooh, those two numbers are negative 2 and positive 1. And then we can factor it. So over here we've got the same problem. I mean, I've shown that this expression right here is a factored form of this one over here. That you can factor it to that, but I don't know how to do that. And then, once you've factored it a bit, you just can't help yourself. You factor till ye canny factor no more. So if I put it in this form, I could factor it some more. Oh my gosh, that is a quadratic trinomial, and those we know how to factor, right? We're looking for numbers that multiply to 4. It's a short trinomial or a simple one, so it's not too bad. 4 and 1 does it. Okay. And if I put it in this form, I could now know its x-intercepts. And that's what we got from the investigation. From that form, I can get this basic shape, okay, that's shown down here. So it really does have x-intercepts at negative 4, negative 1, and 2. It's more helpful in factored form. So the two big questions are, how do we know that x minus 2 is a factor to begin with of this one? And then once we factor out that x minus 2, like if we figured out that x minus 2 is a factor of this, then how do we know that this is what's left over? It's clearly true because we can multiply it out and show that it gets us back to where we started. But how do we generate that process of factorization? Now, it turns out the answer to that question, like a lot of things in algebra, can come from really studying what happens with numbers. So if I take let's take the number 15. Okay? I can factor that number, right? It's 3. And now imagine you didn't know what's left over if you factor 3 out of 15. How would you figure out what this is? 3 times something makes 15. Now, of course, we all know that the answer is 5 here, but where does that 5 come from? That 5 comes from taking 15 and dividing it by 3. That's how you figure out what's left over. And really, the opposite of multiplication is factoring. It's unmultiplying terms. So we can take the same thing with another number. We could take 21, right? You know that it factors to 3 times 7. But really, as long as you know one of those, you can figure out the other one easily. If I know that 3 is a factor of 21, because I know maybe some multiplication rules or some division properties, and if I'm wondering, okay, 3 times what makes 21? Ooh, I could just do some division. Now that seems needlessly cumbersome for numbers, but it unlocks the key to how we're going to do it for polynomials. Division is how we're going to get to factorization. So this section 3.2 is on division and the remainder theorem. We actually won't do a whole lot on the remainder theorem. It's going to require a bit of a trip down memory lane to how you divide it in elementary school. So to start with, we're gonna do some long division. We'll have 171 divided by 3, no calculators. So I would write it like this. Okay. In different places or in different cultures, it may be slightly different. Some places do it like this, and it goes down. Either way is fine, however you learned it, though we are going to, for polynomials, probably take this form that I've written down. Okay, so what do we do first? We go, oh, can I divide 1 into 3? Or in other words, you might say, how many 3's are there in 1? That doesn't divide evenly. So 1 divided by 3 doesn't work. How about 17 divided by 3? Does that work? Yeah. You get 5 3's in 17. Okay. And then you'd have some leftovers, too. So sometimes it's said, how many times does 3 go into 17? 3 goes into 17 5 times, plus some leftovers. Now, you might remember the pattern at this point, but I think it's really important to see what we just did. We divided. Now we're going to subtract something. That something is 15, and it comes from taking 5 times 3. We take 5 times 3 and put it down here, and then subtract. Okay, let's do some more. So that'll leave us with 2, and then bring a term down, 21. Okay, and then we just repeat the process. We ask ourselves, how many times does 3 go into 21? 7 times. Oh dear. Forgot I was still on the eraser. 7 times. Okay, and then we take that 7 and times it by 3. We get 21 and subtract it off. We get a 0 in the end. In other words, we get a remainder of 0. So that is, a trip down memory lane of how you might have approached long division some time ago. Let's try the same thing with division of polynomials, but we won't do long division quite yet. We'll do it the way we did it last year. Last year, you could only divide certain polynomials. Here's what you'd do. If you saw division of polynomials, you might have written it as a fraction. So you'd go x squared minus 3x minus 4 all over x minus 4. What we're wondering is there a nicer way to say this? And what we can do is we might be able to divide out terms on the top and bottom, but only after we've factored. So if you're inclined to do this, 4's a gone, boom, nailed it. That's -2 now. Those are algebraic sins that are quite serious. So instead, what we've got to do if we want to divide out is we've got to factor. Now it's a short trinomial. At this point, I can actually divide out. X minus 4 and x minus 4 are factors on top and bottom. And that leaves me with x plus 1, which is undoubtedly a more elegant expression than what we started with. If you're interested in, say, optimizing computer code, you want the most elegant way of saying whatever operations you want. So x plus 1 is a simpler way of saying this initial statement. But it's got a restriction. It's true that that statement is equal to x plus 1 as long as x is not equal to 4. Why is that restriction there? Because initially we divided by x minus 4, and one of the things in math that you can't do is divide by 0. So if x was 4, we would have divided by 0 and broken one of the laws. Let's try another one. So we're going to try and divide this out. Remember that you have to factor first. You might want to pause the video and try it yourself. And we're back. Okay, so this is still a trinomial. The only difference is it has powers of 4, but it's going to factor the same kind of way. I'm looking for numbers that multiply to 9 and add to -10. And I know that those numbers are -9, -1. This one is going to factor with some x squareds because there was an x4 here. And then on the bottom, now somebody's going to try and divide this out. Maybe before we even do anything else, let's state the restriction. The restriction is that x can't be -3 because you can't divide by 0. Right? So if x was -3, this whole thing would be divided by 0. Now this is a special case of division by zero, but more on that next semester. Okay, we factored a bit. We still can't divide out because we don't have identical factors on top and bottom. Let's factor some more. So this whole first one is a difference of squares. We can factor it as x plus 3, x minus 3. Here we have x plus 1 and x minus 1. And if you're looking for a review on factorization techniques, I'll throw a link in the video description. Now that we've got it all factored out, now I can finally divide these out. And this whole thing turns into x minus 3 by x plus 1 by x minus 1, as long as x is not equal to negative 3. At this point, you might be saying, should I multiply those out? I wouldn't. Factored form is typically easier to work with. In all three of these cases, there was no remainder. In other words, they divided out evenly. 171 divided by 3 was exactly 57. Nothing left over. But that's not always the case in division. So if I think about 233 divided by 5, I mean, you can go through the whole gory process, but what you're going to find is that you get 46 with a remainder of 3. Okay? And what that tells us is that 233 divided by 5 is 46 and 3/5. Okay? The remainder tells us how many over that divisor we still have left. 46 and 3/5. Now here's a weird thing about math notation. 46 and 3/5 does not mean 46 times 3/5, which is what math notation usually means if you have two terms next to each other. What it means is 46 plus another 3/5. So could we have had an alternate way of mathematics developing where we preferred that plus? Maybe. It's pretty elegant to have it here as 46 and 3/5 as a mixed number. But remember, it does mean that whole number plus the remainder. Okay, so what does that mean if we do polynomials? If I divide this polynomial, and you're going to learn how to do this division in a couple of minutes here. But for now, just take my word that it gives you x minus 3 with a remainder of 6. What that would tell us is that this polynomial divided by this polynomial equals this part up here, the x minus 3, plus some leftovers. So think about that last one. The leftovers went on top of a fraction. Okay, so that was the 3 over here. And on the bottom of the fraction would have been the term we're dividing by, x plus 1 in this case. Now, I guarantee you that if you go to a piece of graphing software and you graph this over here and this together, I guarantee you they will be identical. There are two different forms of the exact same thing. Which one is better? Depends on what you want to do. But we've already made the case that division is important for factorization, and factorization is our big goal here. So this brings us to the meat of the lesson, where we learn how to divide polynomials. If I look at this quadratic over this linear, I can try and factor the quadratic and divide them out, but it's not going to work. So instead, what I need to do is use long division. And so let's just think about long dividing some numbers here. If I had 4 divided by, I don't know, 75, something like that. Okay, that would be the same as 75 over 4. So if I set up the form here with long division, it's going to be 4x squared minus 3x plus 1 is getting divided by x plus 3. Okay, let's think about what we would do with numbers. We would take this 7 and we'd divide it by 4. We'd ask ourselves, how many 4s are there in 7? And the answer to that is 1. There's one complete 4 in 7, then there's some leftovers. We're going to do the same thing if we look at polynomials. So I've got a 4x squared, I'm going to ask myself, what happens if I take 4x squared and divide it by x? I'm only going to care about the first term for now. If I take 4x squared and divide it by x, I'm going to get 4x. Just like over here, we were basically going 7 over 4 and saying, oh, that's 1 and a bit. Okay, let's go back to the numbers. The next thing that we would do with the numbers is we'd have to subtract something off. And you might not remember all the steps of long division, but here's what's happening. You'd go 1 times 4 makes 4, and then you'd subtract that. Hopefully that rings a bit of a bell. Let's do the same thing with our algebraic expression. So we'd have 4x, and then we'd multiply it. This time we're going to multiply it by the whole divisor here, all of x plus 3, or the entire binomial. So I'm just doing this off to the side, thinking about it. 4x by x plus 3 is 4x squared plus 12x. Okay? And I would subtract that whole thing off, just like I'm doing with numbers. Now, we're going to do a bunch of examples, so if it seems, pretty abstract, it'll probably be the same thing the first time you saw long division of numbers. After we do a few of them, typically it tends to sink in. Okay, let's go back to the numbers and see what would happen next. So we would have 7 minus 4. We would do the subtraction, and we would bring a number down. The exact same thing is going to happen here when we have these polynomials. So 4x squared, notice we're subtracting all of this. Now some people like to get rid of those brackets and change the sign on every term, as in turn this into a negative 4 and a negative 12x. I find people often shoot about 50-50 on remembering to do that, so I prefer to just leave it like this. Remember, okay, 4x squared, if I subtract 4x squared from 4x, so I'm even going to color code this. What is happening here? We're taking 4x squared. I'm just dealing with this first column here. 4x squared minus 4x squared is going to give us nothing, or 0. So I could write that it gives us 0x squared, but that seems unnecessary, so let's just write nothing. That column is done. The next thing we have to subtract is the negative 3x. And careful here, a lot of people be inclined to write plus 12x, but we are subtracting it, right? So it's minus positive 12x. What does that give us? That gives us negative 15x. So we've subtracted, and if we think about what we did with numbers, we're going to bring a term down. There's the whole algorithm. All we do now is rinse and repeat, and it's been the same way for numbers. Once we get the first step done, or the first sort of iteration of the process done, then we just repeat it. Okay, so let's go back to the numbers. What do I do next? I go 35 and 4. How many 4s are in 35? Or how many times does 4 go into 35? Well, you get 8 complete ones plus some leftovers. Same thing here. We're going to say, what happens if we take negative 15x and we divide it by x? So just worry about the first terms to start with. The next terms will take care of themselves as the process goes on. So negative 15x and divide it by x, you just get negative 15. Okay, back to the numbers. What would we do next? We'd take 8, multiply it by 4, put it down here, and then subtract it. So we'll do the same thing in algebra land. We've got negative 15 times x plus 3, so that's going to give us negative 15x minus 45. Okay. I'm timesing by this whole binomial when I'm going back down. Okay, let's finish it off. For numbers, what would we do? We'd have 35 minus 32 gives us 3. That doesn't divide into 4, so we'd call that a remainder. And in the end, what that would mean is that 75 divided by 4 is 18, remainder 3, or 18 plus another 3/4. Over here, we're going to do the same thing. So we're going to subtract off this whole thing. So you can see the x's are going to zero out. I have negative 15x minus negative 15x. Okay, that's the same as negative 15x plus 15x. You can end up with nothing here. The other one, 1 minus negative 45. So careful here. 1 minus negative 45 is 1 plus 45, or 46. If I try and repeat the pattern and go 46 divided by x, that doesn't work out evenly. So in other words, what we've got, just like with numbers, is our remainder. Okay, so that means that I can finally write my answer. I had a kind of whole number part of the division, and then I had leftovers. The leftovers, or remainder, were 46, and I put it over the x plus 3, the thing we were dividing by in the first place. If I put numbers into either form of this expression, either into the initial or the kind of divided out form, they'll work out the exact same. It's two different expressions that mean the same thing. The last piece of the puzzle here is that it does ask us to state the restrictions, and maybe we should have done that up front. The restrictions are that x can't equal negative 3, no matter what. And that's because you're dividing by x plus 3, and if x were negative 3, then we'd be dividing by 0, and that's illegal. If you're finding this challenging, that's okay. If it doesn't make sense the first time, there'll be a few more examples, and again, you can rewind, you can pause, and you can slow it down. If, on the other hand, this is all sitting well, I'll put a timestamp in the subtitles, and you can skip to that part for the last example, which I think we should all look at. Okay, here's another one to try. So the restriction on this is going to be x can't be 2. Let's set it up for division. It's 5x squared plus 2x minus 3 divided by x minus 2. So that's where these terms go in relation to each other. Let's try doing one with numbers for one example only. Maybe I'll do 5 divided by 623. Okay, just to see what the process is. So the first thing I do is I go 6 divided by 5. How many times does that work? Just once. So the process is 1. We divide, okay, with a single term. Then we multiply 1 by 5. So step 2 is multiply, back in. And step 3 is that we subtract. And then we'll bring down another term. Let's bring down another term. Let's try that with our algebra. So I'm going to go 5x squared divided by x. That gives me 5x. Next thing I do is multiply back in. So if I multiply 5x by x minus 2, what am I going to get? I'm going to get 5x squared, and 5x times negative 2 is negative 10x. Okay, so I multiplied this 5x by the whole bracketed binomial there. Now I'm going to subtract. What's going to happen? The 5x squareds are going to go away, so there'll be nothing here. And then I have 2x minus a negative 10x. That means 2x plus 10x, or 12x. I've pretty much completed the operation at this point. The only thing I need to do now is bring a term down. That is the whole process right there. Divide, multiply, subtract, and bring a term down. Now I just repeat this process. When I'm doing my division, it's just 12x divided by only the first term in the binomial. And the reason for that is that it causes us a lot of grief if we try and deal with both of them. So 12x divided by x is just 12. 12 times this whole binomial is 12x minus 24. I'm going to subtract that whole thing and see what I get. The 12x's should be gone, and they are. Right? I could put a little squiggly, or I could put 0 there. The last piece, it's negative 3 right here minus negative 24. If you're not sure, then write it out off to the side. Negative 3 minus 24. Oh my gosh, that's negative 3 plus 24. or positive 21. And that is your remainder. What we learned is that the answer to the original question is that that division can be rewritten as 5x plus 12 plus 21 over x minus 2. And it has the restriction x can't be 2. I guarantee you if you put a number in the original form and in this divided form, you'll get the same result. I mean, we could even try it. If you put the number x equals 1 into the original form, you would get 5 plus 2 minus 3, so that's 4, over 1 minus 2, which would be negative 1. You'd get negative 4. If I put 1 into the other form, I would get 5 times 1, which is 5, plus 12, plus 21 over 1 minus 2 is negative 1. I get 17 minus 21. Oh my gosh, I'd still get negative 4. There are two ways of saying the same expression. Which way is nicer? Honestly, I kind of like the first way, but if it divided out evenly, definitely the second way would be nicer. So this skill of division is going to help us to factor. We're going to do one more that's just sort of another basic type so that we can get the hang again. And I'll go through it closer to real-time speed and without having a number example on the side. All right, so we've got this one set up. Obviously, the restriction, x can't be negative 1. I'm just going to write off to the side the three kind of steps that we repeat. We divide, we multiply, and subtract, and bring a term down. Down a term. And if we want to use some music notation here, we're going to repeat this process until we can't anymore. Okay, so I'll go 3x squared divided by x. 3x squared divided by x is just 3x. Step 1. The next thing I'm going to do is take 3x and multiply it by this whole bracket. And what's that going to give me? 3x squared plus 3x. Step 3 is to subtract the whole thing. Okay, so the 3x squared minus 3x squared, remember we're subtracting this, gives us nothing at all here. Negative 2x minus positive 3x. Be careful here. That gives us negative 5x because it's minus 2x minus a positive 3x. All right, we subtracted. Lastly, we're going to bring down a term. So plus 5. We have done the whole process, and now we're just going to repeat it. We're right here in the form. Okay, so let me do it again. Negative 5x divided by x. Hey, that gives me negative 5. And now I'm going to multiply back in. Negative 5 by x plus 1 gives me negative 5x minus 5. Oh, be very careful here. So when we subtract, which will be our last step, I've got negative 5x minus negative 5x. That's going to become nothing. Here, I got 5 minus negative 5. 5 minus negative 5 is positive 10. And that's our remainder. So the answer here is just going to be 3x minus 5 plus the remainder over what we were dividing by in the first place. The restriction, if we want to state it, is x can't be negative 1. I'm going to do this one in real time, though, just to show you how quick it can go once you get the hang of it. So let me talk you through this at speed. 3x squared divided by x gives me 3x. Multiply them in. 3x plus 3x. Subtract. Negative 5x. Bring down a term. Now repeat. Negative 5x divided by x is negative 5. Negative 5 times that whole binomial is negative 5x minus 5. We get 10. That's our remainder. Boom, done. Let's write the answer nicely. And that's it. Once you get the hang of it, that's how quickly it'll go. One last one. This one is going to cause us grief. And the reason it's going to cause us grief is because there is not a place for every power of x. So when I look at this, I really need a placeholder for every single one. This means x cubed plus 4x squared plus 0x's minus 1 all over x minus 5. So when I set up my long division, it really needs to have a column for each power of x. Otherwise, you can see that things will get really messy in the actual expression. So I'm going to go through the process now. I got x cubed divided by x. That gives me x squared. Doesn't really matter where you draw it up top because the powers of x will take care of themselves. All right, now I multiply that x squared by x minus 5. And that gives me x cubed minus 5x squared. I carefully subtract. Gives me 9x squared, and I bring down a term. So now I'm going to divide out again. 9x squared divided by x would just be 9x. I multiply this in. So 9x divided by x minus 5 is going to give us 9x squared minus 45x. I'm going to subtract this whole thing off. Some people like to work these out and change the signs by getting rid of the brackets. You're welcome to do that. So I've got 0x minus negative 45x. That will give me positive 45x. And again, I repeat. So 45x divided by x is just 45. Multiply it back in, you'll get 45x. 45 times 5 gives us 225. Remember, it's negative, though. We're going 45 times x and 45 times negative 5. So we get negative 225. And I'm going to subtract this off. Let me just get rid of some of the other stuff up here that I made. All right, carefully subtract. So negative 1 minus negative 225. In other words, negative 1 plus 225 gives us a remainder of 224. So the result to this division is x squared plus 9x plus 45. And I tell you what, the fact that it doesn't divide evenly tells us that x minus 5 is not a factor. This is actually not that helpful for getting this all factored out. Let's call this question D. And the restriction is x is not equal to 5. All we're doing at this point is generating some skills on being able to do some long division. I'll put a link down below for the Chapter 3 Concept Roundup video, where I do a couple of other ones if you want to see another couple that are color-coded and in real time. So all I want you to do for today is work on the sheet that is linked in the video description below with some long division questions. You can do number 1 to 17. It says here, if we were in class, I'd say only take 20 minutes on it. But take as long as it needs to establish some mastery. Feel free, if you've done all those ones, to go back and do the rest of them. This is a key skill. And I often find that students say, oh, I've got to do this step, I've got to divide, and then I've got to multiply. And as soon as we get into that kind of drudgery mindset, then every question takes a bajillion hours. If instead you just go to the question, start doing the algorithm, you can be done with most of these long division questions in 1 minute. Good luck with the material, folks, and let me know if you have questions. Take care.